This talk is purportedly about pat-helland's paper, Beyond Distributed Transactions and Apostate's View. When I was planning this talk, I had this idea for a disclaimer to say that I don't know Pat-Helland and everything. It seemed like a good thing because Pat-Helland and me seems like such a personal title in some kind of ways. But that all got ruined because a bunch of Pat's colleagues at Salesforce, when this went up for the talk presentation, went over to his desk and started harassing him about it and making fun of him. So I've been corresponding with him since then. So instead of having the funny I don't know Pat story at the beginning, I had to come up with this kind of cheesy, but no, now I do know Pat intro. So anyway, this paper is probably one that I talk about with folks more than anything else, and it's partly because it relates very well to what I've been doing for the last couple of years at the company that I'm at. But it's not only that, but I came to realize eventually that I can pull together a lot of the threads in my own personal narrative for what I've done in the tech industry over the last 20 years and kind of thread a lot of it through this paper. So I really love it, and the paper came out in 2007, but I can still tie in things from the heady go-go days of the early 90s when I first started. When there was Pearl Jam everywhere and Temple of the Dog and other things which I'm really glad are gone. My name is Sean T. Allen. I'm the VP of Engineering at Wallaroo Labs. I'm also the member of the Pony Core team. It's a programming language that you probably haven't heard of, but you should check it out because it's awesome. I wrote a book for Manning called Storm Applied. It's about the Apache Storm stream processing system. I spent 2 years on it, and then about 6 weeks after the book came out, Twitter released a blog post disowning Storm and talking about how it wasn't particularly good. So apparently I sometimes make bad judgments about how to invest my time. I'm a lover of graffiti and street art in general, so all of the pictures in here were taken in Paris last summer. I don't know who the artists are, but they're all awesome. So, Pat's paper is about databases in particular, but it's applicable elsewhere. And one of the things I came to realize when I was thinking about Pat's paper is that apparently over the course of my career, I really like to stick databases in things, perhaps in ways that folks aren't particularly used to. This probably started is that when I took a few years off from writing any computer programs or anything when I went off to college and decided that I wanted to be a music major, which, well, I'm here now instead of being a famous musician, so anyway. And when I came back to it, one of the first things that I started using was this development environment called Userland Frontier, and it was a dynamically it's a dynamic language, scripting language combined with an object database. And that really got me that first set off a lot of stuff, which I think comes into a lot of stuff that's come later on for me of this putting databases and things. And I had this idea after that when I was doing development for the BOS, which still, if I had my druthers, I'd be presenting this on BOS instead of Mac OS. But it's whatever I wanted to build this thing that was it was like a web server that there was also a database at the same time, and you could do interesting graph connections between things in it and whatnot. And oddly, if I had more time, I could sit down with you and explain how this relates to Pat's paper, but it's not all that important in the end. And I moved on to stuff like playing around with this Python framework called Zope, which was again, here's an object database, and it exposes objects to the internet and makes them addressable and everything, which turned out to be, well, it was really fun to play with and probably a really bad idea from a security standpoint, but it was an awful lot of fun to play with at the time. And all of this led me to the thing which I think is probably the most important for what I'm building now, without which I wouldn't be up here talking about this paper, which was Gemstone Smalltalk. It's a Smalltalk environment which is a combination of Smalltalk interpreter and a distributed object database. And it is the most joyful, wonderful programming environment I have ever worked in. I have never loved my job more than when I was working with it. And I wanted to bring that same kind of joy to other stuff that I worked on. I started looking around how to do that, and I came back to something which I had first encountered in the 90s, which was the actor model, which Carl Hewitt developed in the 1970s, and started pulling all of this stuff together into what I'm working on now at Wallaroo Labs. And it's a distributed stream processor called Wallaroo. We'll get into that later. But first, I really want to talk about a couple of the key points from Pat's paper. And just dive right into those. So there are some things. We don't have time to cover all of the background, so there's some axioms that you're going to have to trust me on. I have links to an awful lot of stuff at the end where if you want to invest time, you can read more about this. But so this is a talk which is about scaling and in general, in theory, how you can scale stateful applications infinitely. So one of the first axioms, you'll have to trust me on this, is that in order to scale infinitely, you have to scale horizontally. There are two basic types of scaling. There's vertical and horizontal. Vertical basically means I'm going to add more CPU, I'm going to add more memory, et cetera, whatnot to a machine. Although you can add an awful lot of memory and an awful lot of CPU to machines, you do hit some kind of limit at some point where you can't keep adding more, and at that point you need to scale horizontally and add more machines, right? Another axiom that you're going to have to accept for me is that in order to scale infinitely, you have to avoid coordination. Coordination could be, it's basically in order to agree on something and in order for us to make any progress, we both have to decide together to do this. Like John, who I work with, who's in the audience here, if we had to sit there and decide where we're going to go to lunch, right, by getting together in meeting, both of us have to be available, etc. While I'm sitting around waiting for John, I can't really do anything else. It's coordination, nope. So, in the database world, we have transactions. Transactions are a wonderful programming abstraction. They allow me to update multiple things and treat it as though it's an atomic thing. Like if I have two tables in my database, one for customers and one for orders, I can go ahead and I can have a transaction where I update both of them at the same time. And if one of them doesn't update, then neither one of them updates. This is a wonderful thing. When you start to scale horizontally, people would want to keep the same things that they had when they were just on a single machine. And one of those that has been tried in the past is distributed transactions, where I can still have the same type of API and update things differently across the network. You'll have to trust me on this, that this does not scale. Again, in the links, there's plenty of stuff on why distributed transactions don't scale. So, basically what you're going to have to agree with me on is that to scale infinitely, we cannot use transactions, at least not in the way that most people think about them from most databases. And what we've also really said is that, hey, we're scaling horizontally, we have a distributed system, and all of the rules have changed from what we normally have on a single machine, single process type thing. And we're going to have to learn an entirely new set of rules, and we're going to have to come up with new strategies in order to accomplish the things that we want to accomplish, and we're going to have to make different trade-offs than we did before. And in the end, this is really the heart of what Beyond Distributed Transactions is about. So, I've been talking a lot about scaling, and I think it behooves me to really define what scaling means a little bit more, because without that, it's not going to mean a lot. So in terms of the paper and how I'm discussing it today, when we say scaling, what we really mean is that we have more and more things, but those things are basically the same size that they were before. So going back to our customers and orders example, right? the size of a customer, the amount of memory that a customer takes up is not going to really be growing in some kind of large appreciable way. Like if a customer takes up 2 kilobytes of data right now, then a week from now they're still going to be taking up basically 2 kilobytes of data. It's not going to be we now need 2 gigs per customer. Instead, what we're saying is that over the course of time we're going to have more and more customers as our system grows. Today we might only have 1,000 customer records, but a year from now we might have 500,000. And we're really talking about scaling those particular things, the orders, the customers, and everything else. And those things, the customers, the orders and everything, Pat gives those a name within the paper, and he calls them entities. And entities are what we're really talking about scaling. And in the paper, what he talks about is that entities, they live on a single machine. You might have something where they could have replication for resilience or whatnot, but in the end, the easier way to think about it is just there's a single copy of this. So if we have 5 machines which are participating in some fashion, on one machine there will be a customer record for Sean T. Allen, right? And there'll be customer records potentially on other machines as well, but for me, it'll be on one machine. And additionally, only one thread of execution can be updating or otherwise manipulating or reading from an entity at a time. That means that, like, you can't have multiple reads of what is the state of Sean the customer, or multiple things trying to update Sean the customer at the same time. Actually, not trying, because we'll get into that a little bit more. You can have multiple things that are attempting to do it, but we're gonna add some serializability around that. All right, and in the end, then, you know, this is what we're going to expose to programmers, is these entities. And if we step back from that, the entities are things which are defined within our domain, right? Like it could be customers, it could be orders, et cetera. And each entity has a unique identifier. There's some type of key that we can use in order to find that. It could be like a customer ID, like my ID could be 10 or 20 or whatever it might be. It could be a UUID or something that was defined. It doesn't really matter as long as there's a key that maps to this particular entity. And if I want to find an entity, I can use its key. And then entities, unlike what we'd often see like in the database world, or at least the relational database world, where the traditional thing that we do is we normalize data. So we have a table for customers and we have a table for orders, and we can do ad hoc queries or whatnot against them. That doesn't exist in this world where we're wanting to scale infinitely in a horizontal fashion. Entities, as Pat puts it, he says they're disjoint sets of data, and that data resides just in one entity, and that the data doesn't overlap between them. And the reason for this is that entities are bounds of atomicity. Like if we go back to the transaction thing we were talking about earlier, I want to update customers and I wanted to update orders, and I'm going to wrap this up on a single machine database. I'm going to wrap this up in a transaction, and I can make sure that if the customer table gets updated, the order table will also be updated, and vice versa. But if with entities, if we need to update an order and the customer at the same time, they have to be in the same entity together. And so, yeah, what we end up doing is that we end up serializing access to these. So for example, if we have 2 entities, one that's Alice and one that's Bob, right? And we have these different updates or queries that we want to do against them. We're going to line these up in a FIFO fashion, where the first one to arrive is what we're going to execute for each individual entity. But the entities can be processed. Any updates for them can be processed concurrently. So like what we would have happen is like for Alice, right? We have update number 1, and we're going to do update number 1, and it will run in an atomic fashion against Alice and make any changes, and there will be no reads against Alice, and there'll be no writes against Alice while this is going on. This becomes like this is a single threaded system as far as Alice is concerned. We could have 100 threads, but only one of them can be touching Alice at that particular point in time. And you know, from there we can go on and we'll do number 2, we do number 4, et cetera, on down the line. And, right? And this queue, this is the order with which things will happen with Alice. If you are familiar with the actor model of computation, you could think about Alice as an actor and this FIFO queue as the actor's message mailbox. It maps very nicely. If you aren't familiar with the actor model, I'll have links in the stuff that goes later on this. But the important part of this is that we will be going through these in a FIFO fashion for Alice, and at the same time, we can be going through updates for Bob in a FIFO fashion, right? In and out, both of them right there. And really, what we're saying, and I mentioned this before, is that in order to scale, we are going to denormalize all of our data and put it together into these entities in whatever it is that we need to operate on in an atomic fashion. And this can cause some problems. What this basically is this is what you see in a lot of what we would call NoSQL stores, right? I mean, you have a key and you have something, which could be a compound thing, which you're going to look it up by. And in return for your scalability that you get here, you're going to lose easy ad hoc querying, for example, and the ability to say, hey, show me I don't know, whatever it is that you might do. Anything where you would have a secondary index in a relational database, it basically went out the window, right? So the second big idea in the paper that I want to talk about, although there are a few more, and I definitely advise you to read it, is this idea of two-layer architecture. And what Pat talks about is that there are two layers of architecture that you're going to build into a system like this. The first one, which is a top layer, which is what the folks using the system are really going to be concerned with, is a scale-agnostic layer. At this level, all we're really concerned with is business logic and whatever that logic might be, and we're not. This layer doesn't know anything about the number of processes involved in the system. It doesn't know anything about the number of machines, etc. All of that knowledge exists in a scale-aware level, which is down below, and this is where really all of the distributed systems guts would be, right? This is a layer where you can add machines to the cluster. You can remove machines from a cluster. It knows how to route incoming data to wherever a particular entity is. It knows how to recover if there's failure or anything else. And all of this is interacted with through an API, which exposes this in some kind of nice scale-agnostic way, so that my logic, which is up here at the scale-agnostic level, right, my business logic, doesn't have to know anything about the number of processes, et cetera, whatnot, that this is working on, right? And the idea here then is that I can go ahead and I can add more machines to the cluster without having to touch my business logic, because I actually had one more axiom for you, except in this case, it's not really an axiom because I kind of covered it, is that in order to scale infinitely, our business logic has to be independent of scale. If I have business logic which knows that I'm supposed to go look this thing up on the server over there, then when that server goes away, I can no longer scale. Or if I need to start breaking things up and moving them around to different machines as I add more nodes in a cluster, it's also not going to scale. All right. So that's the two key points from Pat's paper that I really want to go over. There'll be a link to it later. It's a very good paper. He has a number of other ideas. I think you should definitely check it out. So, over at Wallaroo Labs, we've actually built a real-world thing that does this. So here's the thing, is it would be nice to say, hey, we went out and read Pat's paper and then we decided to build a thing that was like that, but that's not actually what happened. We were about 18 months to 2 years into building what we were doing when one of the engineers on our team was like, hey, I found this paper and I think I know how to describe what we've been doing. And we read the paper and we're like, oh, that's what we've been implementing. Now, we might have, one of us might have previously read the paper and we started doing it, or maybe it's the thing you would want to do if you do it, but I don't know. But yeah, we've been building this thing, which is a scale-independent computing basically for Python. What we have is a stateful stream processing engine where you can kind of imagine, hey, I got a stream processor, but I've stuck some kind of weird database in it in order to keep state, except it's not really a database. Well, I mean, it manages state for you. It allows you to query it and update it, but not in a way that most folks would consider database-like. But it's actually there. But it's a real world example of scale agnostic. And really, I'm going to go through like a little bit about how it's scale agnostic. And then if you went out and wanted to build a scale agnostic system, which I hope folks will, because I think it's a great way to do things, some of the various problems that you're going to run into and going to have to solve. So a couple differences if you take a look at Wallaroo stuff. We have entities, but we call them state objects, but they have all of the other stuff. They have atomic units of updates, and they have unique keys within a namespace, et cetera. We also have the two-layer architecture, but we call it scale independence instead of scale agnostic, where we have the same two layers where we have our user-supplied logic. In this case, it's logic that folks write in Python, which in order to do like data processing, and they write it using to our API, where our runtime, which knows all about the number of machines that are in a cluster, et cetera, can take whatever the user logic is and map it out over any number of machines. And you know, there is a lot of hard stuff that if you want to build a system like this, there are a lot of problems you're going to have to solve. A lot of them are general distributed systems problems in general, but at least in our particular case, it got even harder because it's a framework. So I'm going to talk about a number of different things that you're going to have to deal with, but it's not like there's not a right answer for any of these. These are different things you're going to have to decide. Where do I want to fall on this? And they're like spectrums of things. For a concrete example, the CAP theorem. If you don't know what the CAP theorem is, or you've read maybe a really bad explanation of it, because there are lots of them, probably as many bad CAP theorem explanations as there are like Haskell monad burrito tutorial type explanations. But the CAP theorem basically comes down to is you're going to have to make choices in a distributed system between consistency and availability. And consistency really means that if 12 people ask, what is the value of foo? How many of them are actually going to, are all 12 of them going to hear the same value for foo? Are they going to hear different values, et cetera, or whatnot? If everybody hears 12, then you probably have a very consistent system. But the more consistent your system becomes, the less likely it is to be available. So if you have like a network partition where your cluster is in two different, it gets split in two, what do you do at that point? If you want to keep running, then you're going to have to allow updates to at least one or both sides of that, where not everybody is going to be able to see the same results, right? You can't get away from it, and you're going to have to make decisions on that. Another one that you get with distributed systems in general, which you would apply here, is you have to decide what kind of message delivery guarantees that your scale agnostic, your scale aware underlayer is going to provide, right? Failures will happen. Like TCP is really nice and reliable most of the time, but it will still end up losing messages. You'll probably almost never notice. Most people probably don't do enough testing of their applications to ever notice TCP when it does have one of those weird things. But you're going to have to decide, if a message gets lost, what do? If we don't resend it, then the term for that is it's at most once message delivery, right? We sent it in, hey, either it got there or it didn't. There's at least once, which means, you know what? I'm going to keep sending this to you until you tell me that you got it. And that can always be really interesting, because you might have sent it 3 or 4 times and the other person might have got it 3 or 4 times, but the acknowledgement coming back to you, you might not have seen that. And from there, there's a whole variety of like things that are going to come from that in terms of what does this mean now? I'm duplicating messages to you. How do we work that out? There's also, so exactly once is probably the worst term in computer science, I think, at this point. Anybody who starts a discussion of exactly once without defining exactly what they mean by it is basically just asking for the entire internet to come down on their head. So I'm just going to say that there's some terms that folks use. Sometimes they say effectively once. Some people say exactly once and mean the same thing as effectively once. They spend a lot of time on the internet arguing with each other about things where if they just defined their terms, they wouldn't necessarily be arguing anymore. But the basic idea here for either one of these is that if I'm going to resend messages, right, then the system should treat it like that message was only sent once and it arrived, right? That's generally what people mean by effectively once. That's sometimes what people mean by exactly once. But you have to make these decisions, and if you want accurate results, then you need to provide something that's like this. I can resend messages, but the processing that's on the other end of that will only happen one time. Otherwise, like if I'm keeping count of things and you're saying, add 1, add 1, add 1. Instead of getting like the value 3 like I'd want from that, if I had to resend some, I might get the value 10 or 20 or who knows. And if that's not bad enough, oh my God, this message ordering. Oh Lordy. This is a really fun one, especially when you put it with another one that I'm going to talk about later, which is performance. Because one of the nicest ways that you can go fast is say, you know what, I don't really care what order you sent messages to me in. I'm just going to process them in the order that's fastest for me. But if you do that, then you might break ideas that somebody has within their particular domain, right? If I say, hey, here's a deposit of $20 into my bank account, and then here I'm going to spend $15 out of my bank account, and you process them in the opposite order, you might have just completely screwed up the business logic for something that's there, right? It's like, oh no, wait, sorry, you can't spend that $15, you have $0 in your account. So you're going to have to make some kind of decisions on what is the ordering of messages, and then hey, this is at least moderately okay to deal with so long as you don't have failures. But the moment you have failures, it gets even more fun when you're trying to combine, message ordering and failures and performance. It can be really hard. And then, okay, local knowledge. John, who's in the audience, he gave a great talk yesterday on local knowledge. If some of you saw it, that's awesome. You'll be really up to date on this. I'm going to mostly gloss over this. But if everything within a system has to agree on what the value of something is, that is coordination. And you're going to have to do it at some point within your system. You can't ever have completely local knowledge, but as much as possible, you want everything within your system, computers, the things that are going to be doing routing and everything, to be able to make a decision purely on what they know. If I have to go out and ask another machine, hey, can this person deduct $15 from their bank account? I'm going to be waiting the entire time for that. I need to be able to make that decision right there and now if I want to be able to get the performance that I need. And even if you're in the camp of, well, it's fast enough, the problem is as you give up more and more performance when you're trying to do this, that lack of performance also starts to cut down on your ability to scale horizontally because you're adding more and more overhead to this. And you're basically effectively trimming down infinitely to the more reasonable world of, well, as best as we can given all of the constraints that I put on this. And of probably all of these, this is the one that you have to build in the most from the beginning. You can't really refactor your way into this. The first version that we wrote of Wallaroo, well, the second version. The first one that we did was written in Python, and it could process about 20,000 small messages a second. And we wrote our first version in Pony, which compiles to native code and everything else. And we're like, woohoo, this is going to be great. It's going to go so fast. And it did about 15,000 messages a second. And it was, because we had changed the design, we'd made it multi-threaded, and we had put this one big giant point of coordination within each node where everything had to go through it. And it was slower, and we spent 6 weeks, 8 weeks trying to refactor our way into it before we finally threw up our hands and said, no, we're just going to rewrite the entire thing. We're going to throw away the 5 months of work that we did on that, and we're just going to start over. And 4 weeks after that, we had a system that was able to process about 3 million of those messages, right? You can't really refactor your way into local knowledge. You have to figure it out beforehand. If you build a system like this and you haven't before, play around with some prototypes where you know you're going to throw them away. You're gonna. The thing you have to figure out is what are all the moving pieces inside of here? Where are the ones which are in a hot path, and how can I make them operate using local knowledge? From there, you have to worry about the programming model and what you're going to expose to the end user, because, well, one, they're going to have a lot of they're gonna bring a lot of expectations that comes along with it. And when you're talking about this, you're talking about a thing which manages state at this point. So what does state look like? In Wallaroo, we decided, we reversed course from when we started. We were like, what we're going to do is we're going to provide people with CRDTs. If folks aren't familiar with them, they're basically they're data structures which are good for being able to work in a distributed environment where they can slowly converge on a value. And we thought this was great, but you have to define for each data structure, you have to define a CRDT, and there's like some ones like, hey, here's a counter, here's a hash, here's an array, et cetera. If we see an add and remove, what happens, et cetera. And there's a lot of rules that go around and everything, and it can make it much easier for your system to handle things like replication, failure, et cetera. On the other hand, you've also given the application programmer a much more constrained set of stuff that they can work with. So what we ended up doing is we decided, even though it's a lot more work for us, we're going to provide opaque data structures to the application programmer there to allow them to pretty much describe using any data structures that they might have, how they want to do it. There's a trade-off here with that in terms of what can be expressed by the programmer, how easy it is, like I said, to replicate stuff, how easy it is to recover from failure. And in the CRDT case, in a lot of ways, it would actually make your performance a lot easier if you were to constrain what the application programmer could do. Performance in a system like this is going to be incredibly hard. Like local knowledge, you can't really refactor your way into it. It's just a thing that you have to be like keeping your eye on from the beginning. There are so many areas of performance you'd have to worry about. I would say this, if it's not in a hot path, then who cares? Just don't worry about it, because you're going to spend so much time like obsessing over, oh my God, this thing is in a hot path. How do I make it use local knowledge, et cetera? How can I optimize this one little bit, that you're not going to have time to worry about other stuff. So if you end up using global knowledge for an event that only happens every, I don't know, like if you need global knowledge in order to add or remove nodes from a cluster, great, go for it. Because people probably aren't going to be sitting there like every second adding and removing machines from a cluster. If they are, you'd probably want to ask them what evil thing they're doing to your software. It would probably be Kyle Kingsbury running Jepson on it or something like that. Yeah, I mean, you shouldn't be seeing that all the time in the real world. And the performance stuff is going to be so hard, you should just focus on it elsewhere. Network overhead. Whew. Oh, I hate network overhead. Yeah, like when you're in a single machine system, a single process system, you can keep everything in local memory and it's really happy. Maybe you want to run more than one process, but you're on the same machine. You can do some awful thing with shared memory, perhaps. Who knows? I've done lots of awful things with shared memory in the past. But the moment that you start sending out stuff over the network, that's definitely going to be slower than local memory lookup, and hopefully you're even just reading stuff from your local disk is faster, although that really depends. And that latency is really going to add up. And if you want to run on stock hardware or something, at a certain level, there's not a lot you could do about this, right? Like you can do some network tuning, et cetera, and everything. But if you want to get a lot faster, you're probably going to have to start playing around with like kernel bypass stuff or whatever, which is almost always a bad idea, but occasionally a good idea. If you don't know what kernel bypass is, then don't look it up because it's a bad idea. You just probably don't want to do it. But yeah, and the absolute worst thing which comes in with the network overhead is serializing data. I read a paper. I tried to find it to put into the links that I had. Unfortunately, I couldn't remember. I'm not real good with Google, and oh my God, data serialization is awful. Doesn't really get you a lot of like correct results. But there's a paper where they were looking at where performance goes in Hadoop and Spark. And it was something like 30 to 40% of the time in a Spark or a Hadoop cluster was spent serializing data to send from one node to another, or deserializing that data when it was received at another one. And you can see this in a lot of systems, like when I used to run a Storm cluster, switching from using default Java serialization to using Cryo gave us it was like a 10% like speed boost just from that, because there's so much time that's spent in it. You're gonna spend a lot of time in that. You can tweak it, you can try and find ways to do it, but there's not really any way around it. Because like, hey, data is going to arrive from some external client and you need to process it, and you're going to have to do at least some level of deserialization to get enough information to figure out where this thing needs to be routed somewhere else in a cluster. Or your client's going to have to know that. And either way, eventually at some point, you're going to start getting a lot of overhead on this. And it just, yeah. Oh, wow, I actually sighed. That was, yeah, there we go. So, a couple other things we don't really have time to talk about. Knowing that the thing you've built actually works, that's an entire another talk. I have a link to a talk that I gave for how we go about doing it. That was 40 minutes. I think I touched on maybe 1/10 of what you could learn about it. Kyle had the great little bit about Jepsen earlier. That's like one tiny fraction of what you can do. But yeah, like knowing that you've actually done this and that it works, and does this work when there are failures, and are the guarantees that I'm telling people about, do they really actually exist in the system, is incredibly hard. And I would advise that this is probably the first thing that you should do if you're going to build a system like this, is build a test harness first, and then start putting your thing inside the test harness. Because if you don't, you're just going to be in a world of pain. You're going to invest a lot of time on performance and everything else in order optimizing that, and then you're going to find out that your thing just doesn't actually work, and you need to start over from the beginning. Yeah, so one last thing, just to let you know, I've been talking about this in terms of, hey, distributed system and all the wonderful guarantees, you know, that you lose from being on a single system. Your multi-core computer is actually a distributed system. It's just hidden from you a little better in the, if you want to call it, you could say the network interconnects are more reliable. But yeah. There are all sorts of things that can happen with data races, with cache lines, with everything else, where you have two CPUs and they actually kind of like, they have different views of what's going on with data. And most of the advances that we've got in CPUs over the last 20 years, most of those were playing tricks on things, and they actually violates your expectations of how a computer would work. But that's another talk. I probably will do a ranty talk someday about how we should have just stuck with mainframes and we all would have been better off. But that's really, that is for another day. Thank you. I'm really at the end here. There's a GitHub repository where I keep making updates to it to put more stuff in. Almost everything that I talked about is in here. From Userland Frontier and BOS to Pat's paper. You can find Pat's Twitter in there. That's great if you want to follow. He doesn't ever actually tweet, but you can still be like, hey, I'm following Pat. I'm following Pat even though he doesn't tweet. Yeah, I don't know. I'm just thinking about the puppies now. So yeah, thanks.